out below that represents the passenger compartment. Draw and label the forces that are act on the passenger compartment when it's at point C. So when it's right here, what forces are acting? So of course we have gravity going straight down, and we have Fn. Now where do I? Of course, am I missing Fc? Right? Centrifugal force? No. Well, what's making it move in a circle? Isn't centripetal force making it move in a circle? So we said anything in the universe moves in a circle, and it's moving in a circle, right? The sum of the forces is F sub c. Yeah, very good. Okay, the key is this is the sum of the forces. You should never, on a drawing, have something labeled F sub c, because it is the result of everything, right? So what is causing this thing to move in a circle right now? Fn, normal force. Does that make sense? Oh, is there friction? Okay, cool. Okay, questions on that part? Okay, and just so that I can keep things on a short leash, we'll take a look. That question 1. Okay, this is question 2, right? Okay, so we're good for that. All right, next, part B. What's that question? In terms of theta and the magnitudes of forces, determine an expression for the magnitude of the centripetal force acting in the compartment at point C. So what is the centripetal force? Yeah, so we're just going to say, we're going to set everything equal to mv squared per r, right? So then what they're doing is if you look at this object, like this, oops, put it straight down, they're just taking this as Fn, right? And this, do you see at this moment, F sub c points this way. You get what I'm doing by that? By drawing it like that? You can see what I drew over there? Oh, that was disgusting. Oh, it snuck out quick. Right. Don't go. Yeah. There's nothing.
Breathe, John.
I don't know. I sneezed in your face. Okay, so I was reading, I was listening to. There's actually quite a few people who are coming from the viewpoint that using Purell and all that crap is actually not good. Like they said, maybe it's okay for old people. Like it's good for old people because their immune system is like done and it's decaying, so there's nothing that they can do. But they said like my sister-in-law is a nut with that stuff. And like, I mean, if her kid like pushes a door open, then she's like on him and like sanitizing his hands. And I think that's really bad, isn't it? Yeah. Like, so is his gist that you shouldn't do that? Yeah. I mean, obviously, if a kid freaking picks up a dog turd, okay, fine. All right, we need to sanitize that situation, but yeah.
You need those kids.
Yeah, exactly. Okay, yeah. Yeah, right? Like kids should go play in the dirt and stuff. Yeah. I wonder if like the number of people who are allergic to like things and all that stuff, and you know, like now schools can't even serve peanut butter anymore. Because like so many people have peanut butter allergies and like they could die.
Why don't they know? I'm sorry, but didn't you know that people peanut butter are allergic to?
Yeah, and you know, it seems like, aren't there some people who are so allergic to peanut butter that like they can't even be in the same room with peanut butter?
How do you live? How kind of without
Well, see, I mean, this is the weird thing, right? Because the more, wow, this is gonna sound
That
very.
is hell on earth. Life without food.
Well, the thing is, it's just gonna get worse, right? Because we keep fighting natural selection. Because natural selection would trim the human genome and ensure that the strongest and healthiest people survive. But we don't let that happen. I mean, obviously, I'm not saying we shouldn't. Yeah, it's survival of the fittest, but it's kind of interesting, right? Like we keep allowing genomes that have problems survive and propagate, so that those things like kind of diffuse through the population, so that you get more people with like diabetes and more people with cancer. Because like 100 years ago, anybody who had cancer died. You just died, and you died for whatever, like something. And so then like the people who have cancer-resistant gene pools are the ones who live. But then now, yeah, it's weird. I don't think we should like just have survival.
discrimination?
Oh man, that's recorded. That's terrible. Okay. Somebody's gonna come back to me and say, "You eugenic bastard." Eugenics is like this sort of theory of like natural selection, but for humans. So like you do things like really brutal Nazi things. Like you find people with inappropriate or insufficient gene pools, and you neuter them so that they can't have children. Yeah. I mean, you don't kill them; you just neuter them.
It's not as bad as neutralizing.
Yeah. And I don't mean like, it's like maybe chemically or something. All right. Well, anyways, so like if we take this as theta, then this is going to be mg sine theta, and that's where they get this. So do you see that f sub c is equal to fn minus m? Oops, just kidding. They obviously use this as theta. Because they subtract this. Because if we have that theta, it would be mg cos theta. Right? So does that make sense? The subtraction of those two? And then all they're doing then is that they're just saying mv squared over r is equal to fn minus mg sine theta. Whoa, look at that. All the variables got screwed up. I think that's delta.
D. What the? It's really weird.
I don't know. I was looking at it last night. I didn't know.
Okay, so let's see. Oh, okay. So this is the answer. Right? You don't have to go any farther. This is just the answer. Then this is an answer that uses energy. So they're talking about the potential energy is equal to the kinetic energy. See, do you see what they've done there? And so this is supposed to be, I don't know what happened here, but this is supposed to be V. So it's mv squared, 1/2 mv squared. So then what they're doing is they're saying the v squared equals this because the masses cancel. And they're getting a statement. We get a statement for that's weird. That's a lot of algebraic gibberish. It's like they're using the initial statement, then they get this, and then they're saying since f sub c is equal to this, I can take this v squared and plug it into there, and then get this as an answer. So this is like algebraic gymnastics. You don't have to worry about this. Does this statement right here make sense to everyone? Okay, good. That gymnastics one is kind of weird. All right. For C, derive an expression for the speed of passenger compartment as it reaches D in terms of mr. Was that? We weren't looking at C, were we? No, C is down there. All right. Yeah. So if we're looking for an expression for C, right? We've got PE up here, and then we've got KE down here. Do I just put P equals KE? No? What else do I need to put? Yeah, so it looks like we can just put P equals KE. It's not rotating, right? It's not, it's not rotating. It does have circular motion, but it's not rotating. So we can just say the PE equals KE. And then that's just the statement, right? That's supposed to be mg delta H equals mv squared, 1/2 mv squared. And that's what we said here. So this PE is mgh, 1/2 mv squared. Right, that goes away, so v is the square root of 2gh. And then h at this point, c, yeah, we have to like come up with this. So h is equal to 3/4 r plus r sine theta. Does that make sense to everybody? What happened? No, this is just how far did this fall like this? So this is 3/4 r, and then this little piece right there, it's that part. But that's not exactly r sine theta, that's a problem. Because it's like this. This is r, and that's theta. So how do I find this? Wow, that's annoying. Because this is r cos theta, and this is r. Oh no, yeah, that is r sine theta. Okay. Sorry. Yeah. Sorry, what's that? Oh, they did? Oh, that's easy then. It's just r. Sorry about that. I was calculating at point C, but if they wanted it at point D, then it's just P equals KE, and then the PE is this whole height, right? That's R, and this is 3/4 R. So that means mg, and then h is whatever, like 7/4 r. Yeah, equals 1/2 mv squared. Okay, sorry about that. So I was calculating the height based on the wrong position. Yeah, they just did 7/4 r. Okay, so we got the idea right, so that's good. Then, oh yeah, point D. A force acts on the compartments between D and E and brings it to rest at point E. If this compartment, is this an AP Physics C question? Wow. This is like the easiest question I've ever seen in my life. Sorry. What I'm sorry. What I should have said is, hey, there's no calculators. All right. Yeah, sadly, my insert foot A into mouth B is low. All right. So if it's brought to rest by friction, the numerical value of the coefficient of friction. Here you could use calculus if you want, or you could just say the work done by friction is equal to the change in kinetic energy. You do that, which is also equal to the initial potential energy. We want to do that, so that's going to be F sub F D is equal to mgh, mgh, which of course is 7/4 r. And then this F sub F is mu mgd, which equals mg and 7/4 r. So that goes away. And so we get mu is equal to 7/4 r over d. Let's see if that works. Oh, nice. have something different. They have oh, is there something in the drawing that shows us? Oh, okay. All they did, so my answer was mu is 7/4 r over d, and then what they're telling us here is that this is d for me. So if d is 3r, then I can plug that in there. So I get mu is equal to 7/4 times r over 3r, and so I get 7/12, and that's the answer. All right. Any questions on that problem? Okay, that was. But I mean, oh, so okay. When you said you didn't, was it? I thought you were saying you didn't understand the energy explanation of this one thing, but you got this problem. Yeah.
Oh yeah, it's just I don't know.
Oh. Everything's variables.
Yeah.
Yeah. Okay. So then we can go to our E&M. Huh? Oh, did I miss a part? Oh, part E. Okay, here we go. All right. So no friction, braking force, or Dave's constant is velocity. Well, okay. This differential equation, right? They just want something. They want this solved for v of t. So right away you can say that the sum of the forces is going to be ma. So it's going to be negative kv equals ma, and then break a apart, right? Because a is dv dt. Oh yeah, you probably could have done that too. So what they did, they just used the sum of the forces equal to ma, and then they did this. That's what I would have done. Right? So what they did is they said the sum of the forces is equal to ma, so negative kv is equal to ma, which is equal to m dv dt, and then so we can kind of separate it up into the two statements. So that's all they did. So they're just saying this is negative kv equals m dv dt. They didn't even break it up. I mean, I probably would have said negative kv over dv is equal to m over dt, but they didn't even break it up. Okay, then solve the differential equation that you wrote. So to solve that differential equation, okay, what they did was you need the dv on top. So I would have moved them and then flipped it, but they flipped it first. You get what I'm saying? So they have negative kv equals m dv dt, and so then they moved everything so that obviously the dv's have to be on top. So then I don't know. I just did it kind of like this, right? Keep this and then flip this. So you get dv over negative kv is equal to dt over m. And then that's what they got here. They just moved the constant onto this side. So they put this negative k over here. So you get it dv over v, and then that's the natural log of v, right? And that's going to equal negative k over m times t. Now this is a natural log, and it's from Oh, v is the velocity at point D. Okay. Oh, okay, that's cool. And then this v is whatever the velocity at that moment. So they're taking v sub d and v. So then that's where they're breaking it into these two things. The natural log of this is equal to that. And then taking both sides to the e. And that's where they get v over vd is equal to e to negative kt over m. And then their final expression, which says v is equal to v0 e to the negative kt over m. Now, actually, we need to pay attention to this because this is an important use of the differential equation, right? So, how did all of this start? They said write a differential equation when you know the sum of the forces is negative kV. Sorry, that u is messing me up. But okay. So then I know that this means the sum of the forces is ma, right? If you know that if you're supposed to come up with some sort of differential equation, always just think about what is a differential equation is always relating to like the time rate of change or the displacement rate of change of something. Since they asked for velocity, then I should be thinking, well, what is the time rate of change of velocity? Boom, acceleration. Sum of the forces has acceleration in it. That's how I get that statement. And then this statement translates to this. That statement translates to negative kV is equal to m dv over dt. Okay? And so then, now it's just a function of getting the v and the dv together and putting the rest on the other side. So then, the easiest way to do that is to just move all the other variables. So we get negative k over m dt, and then that's dv over v. So that's kind of like our differential statement right there. Now, how do you solve this for v? How do you get a velocity, like a statement that describes the velocity? So that's where you take the integral of both sides, right? And then the integral of v to the minus 1, right, is the natural log, right? And so then we take the natural log of that. Now, what we're doing is we're saying that we're taking it from vd, or the velocity at v, or at, the velocity at d, to some other random velocity that we're interested in. You know, some final velocity, if you will. Or if you want to call it velocity at e, or whatever you want to, well, no, this is stop at e, whatever. At some velocity at any point in between. So when I take that integral, that's where I'm getting the natural log of v minus the natural log of vd. And then that's giving me, over here, just that's equal to km over t, or km times t. Oh, 0 to t, sorry, that should be 0 to t. Yeah, sorry about that. Because, and the reason we can do that is these two things are happening in the same interval, right? Vd to v is the same thing as 0 to t. Okay, so that's where we get this from. And then now the question is, how do I get this v out by itself? So then I take both sides, right, e to whatever. And then that allows me to get v, the minus becomes divided. So v over vd, and then that equals the e to the negative kt over m. And then I can get v is, I think that's v0. But yeah, times e to the negative kt over m. So this process in your head should be highlighted by certain things. First of all, identify it when they want you to come up with the differential equation for a certain variable. Look for the time rate of change that relates to that variable. Right? The bridge is that concept that says, okay, the time rate of change of what they want. What is that? They ask for velocity. So the time rate of change of velocity comes from that acceleration statement. Right? And that allows me to make this, like the dv dt, and get this statement here. And then after that, it's pretty straightforward. Well, they told me the force was negative. They said that's the stopping force.
I see.
Okay, well, I hope that made some sense. Solve the differential equation on x as well as sketch a graph of the magnitude of acceleration. Said that. Okay, so from there, I mean, it's just a exponential sort of decay thing as it approaches zero. Right? And then that just comes from the graphing what we already just did. Okay, so this thing, magnitude of the acceleration. Well, if you just look at your expression, if we go back, let's see. I guess the easiest way is just to like this velocity statement. If you take the derivative of that, and that's their logic here. That the acceleration is going to be the derivative of this velocity statement, and then that gives you this acceleration. And then the exponential comes from that. Yeah. Why is the magnitude acceleration never get to zero? Alan, I'll take a look. I'll try to look into it further and find out why, and I'll come up with something tomorrow. But I want to go ahead and do the E&M one today before we leave. Okay, so let us move on to E&M. Okay, this one. So, calculate the value of the charge on the bottom plate of the capacitor a long time after the switch is closed. So, S1. So, that should be pretty straightforward, right? Because after a long time, what happens to the current? So, I should just be able to be C is Q over V, so Q is equal to CV, right? And that's because after a long time, the current goes to zero. If the current is zero, then Ohm's law says that there's 0 volts across that resistor. And then that's why I can say Q is CV. Right? Then I'll ask to sketch a graph of the magnitude of the charge on the bottom of the plate as a function of time. On the axes explicitly labeling intercepts, blah, 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 blah. So then the charge that's on the plate should be a function of the current. And we know the current changes exponentially, right? It decreases. So then that should allow us to get something similar to the graph that we just did. Yeah. So it goes up and approaches that. Because as the capacitor begins to get charged up, like if it was a graph, well, okay, wait, you said why is it not like this? Well, because if it was like this, that would mean like the limit is there, right? But that's not the way it works. Because what happens is that it begins charging, and as it fills up, the current slows down. Yeah, and so as the current slows down, it gets closer and closer to the goal. Okay. So that same question, Ellen, is here, which I need to figure out why that's the answer. Because this is an asymptote too. Yeah, I mean, like, on the other question, if it's decelerating, then, and if the deceleration is a function of velocity, then it's going to approach zero as the velocity increases. So because the acceleration, I would say that limit is there because the acceleration is a function of velocity. And if velocity is zero, then it negates the acceleration. So let's see, you did. Yeah, I think it has something to do with that. In the same sense that this has something to do with that the maximum charge is the asymptote. In the other one, the asymptote is zero because the acceleration is a function of velocity. So as the acceleration approaches zero, it's making the velocity approach zero. That would be my initial guess, but I'll try to look at it more and talk about it. All right, so then, is everybody here okay with this? Is everybody here okay with that? And understands why that is that way? Okay, good. Then, sketch the graph of the current through the resistor as a function of time. Blah, 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 blah. So the equation for current, we kind of already know that. That's that I equals I0. Right? We know the current decrease. Okay, so hopefully we can see this. Oops. The charge builds up to a maximum, but the current decreases to a minimum. What? Yeah, it's the current through the resistor. Yeah. Because that's what, yeah. Sorry, I drew this incorrectly. It should have been like 0. Right? There can be no current until that turned on. Or whatever, something like that. What's that? Yeah, it's just like this. Because there's no charge, and then and then this one there's no current until the switch is closed, and then the current decreases. Okay, so we move on. In experiment 2, the capacitor is uncharged, and the switch is closed to position of S1 at time. The switch is then moved to S2 at time 2 when the magnitude of the charge of the capacitor is this. Allow electromagnetic oscillations in the LC circuit. Calculate the energy stored in the capacitor at time t2. So this first part, the first question is pretty straightforward, right? Because we know that the energy in a capacitor is 1/2 CV squared. Okay, so that's easy. And they've already told us the charge. So you can do this any number of ways if you want. You can just like P equals IV, you can solve that different ways. You can also solve CV squared different ways as well, because C is Q over V, right? So you can get 1/2 QV. You could also say V is Q over C, so you can get 1/2 CQ squared. So you can use any one of those to get the right answer for that. Then calculate the maximum current that would be present during the oscillations. So if we know, let me double check that, let me make sure that's right. Yeah, okay, so it's whatever you want to use to get your answer there. And then now the last two, like part 2, is just a function of using the, interesting, they use the energy. Oh, that makes sense. So what they do is they use the energy in the inductor to get the maximum current. So when there's no charge in the capacitor and all the energy is stored in the conductor, then that must be true. And then they use the energy on the capacitor, set that equal to the energy in the inductor because the system oscillates, and then that's how they calculate that current. That's interesting. To be honest, I wouldn't have thought of it that way. And then the third part, calculate the time rate of change of the current when the charge in the capacitor plate is 50. So the time rate of change of the current, time rate of change of the current is the time rate of change of the charge. Yeah, this is actually something that's kind of interesting. This right here, if you're ever in a circuit problem and you don't know what to do, it seems like the loop rule is always the solution, right? It's like when your back is against the wall, and you're like, okay, I don't know what the actual, like any of the values at any given time, then the loop rule seems to usually come into play.
Teachers, please pardon the interruption. The testing for AP Spanish language is taking place today. To accommodate the speaking portion of the exam, bells will not ring from 10:08 to 12:06. So again, the bells will not ring from 10:08 to 12:06. The bell schedule will resume ringing at the end of the lunch period and will continue for the rest of the day. For the time frame in which the bells are off, please pay attention to clocks in the classroom for dismissal. Thank you for your patience and support. Have a great day.
Yeah, they should have like a visual bell system. Yeah, like flash, like some sort of flashing light thing, or like and you can totally trigger it with like ultrasonic frequency. Right? And then you can use it for crowd suppression if kids are being idiots. Because they just pick a frequency that none of the teachers can hear, but then it just hammers you guys. It's like, quiet! I'm just kidding. Okay, I'm kidding. All right. So what they've done here is they've said the inductor capacitor circuit. Right? This circuit, the loop rule says it has to be 0. So they just use the expression for the voltage on both, right? Because C is Q over V, so V is Q over C. That's where they get this from. And then this one, the induction times the change in current as a function of time, that's the voltage on an inductor. That's the voltage stored on an inductor. So then it's a function of just setting them equal to each other, and then that's it. So this one is, do you remember that L di dt is equal to V? Is that in your formula sheet?
Yeah.
Okay, well, there you go. So if you just looked that up on your formula sheet, then you would have had it. Okay. Sorry?